All right. Well, hi, I'm Josh. I'm going to give a two-part talk on superdensity and bounded geodesics in moduli space. But before I start, I want to say thank you to the organizers for inviting me and letting me give this talk. I'm definitely excited to talk to some of y'all throughout the week, and either on the Discord or one of the events that's happening. Cool. So I think I'm going to start by putting a theorem for writing down the theorem that I'll prove in the second part of this talk, just to give you a sense of what's going to be happening. And then I'm going to spend most of this talk defining and motivating kind of where this theorem comes from, or defining some of the words in this theorem, and then kind of motivating where maybe this comes from. Okay. So we're going to say let omega be a translation surface if the associated Teichmüller geodesic is, let me just kind of write the notation, in positive time. This is bounded in the moduli space. Then the linear flow on omega is something called superdense. So I have a lot to sort of define for you. So let's just kind of start with that. So I'm going to give you a definition. So for those of you all familiar with translation surfaces, many different definitions I could give that are all equivalent. I'm going to give one that will help most, I think, with understanding the proof of the theorem later. But then I'm going to sort of suggest an alternative. We're not going to go into the alternative definition or why these are necessarily equivalent, but it will at least sort of help a little bit with well, understanding where my notation's coming from. So first, let's define a translation surface like this. So a translation surface is a polygon or polygons in the plane C such that each side of the polygon is identified to a parallel side. Okay. And in addition, there is a, we'll just say it kind of like this. So there's a choice of north, or there is a specified direction that we call north. Let me write it like this. There is a specified north on the surface. So let me give you an example. This has just become my favorite example. Fairly kind of straightforward. So here we have a polygon that's tiled by 3 squares. This is actually a special kind of translation surface called a square tiled surface. Here I'm going to identify these edges by translation. So I need to add this to my definition. So this identification that's happening in the polygon is happening by translation. So this side is identified to this side by translation. This side is identified to this side. We have that side identified to this side, and this side identified to that side. Cool. Now, here there is sort of a natural north that we can pick, which is kind of up in some sense. It's up in the sense that this is sort of living inside of some C, or I'm thinking about it as a polygon living in the plane. So the positive imaginary direction gives me sort of a specified north direction. Cool. So this is, in some sense, it's a flat surface. So once you make this identification, you get this sort of compact object that's flat. But it can't be completely flat because of Gauss-Bonnet. So let me just identify the, well, an accumulation of negative curvature. So if you think about what's happening at this point here that I just highlighted, let me actually do it in slightly different color. If you think about this point, that point is the left side of the edge I labeled 3, which means it's the same as this point. But that's the top of the edge that I labeled 1, which means it's the same as this point, which is the right side of 3, which is the same as this point. So I can kind of keep doing this. And so this is the left or the bottom of 1. That's the top of 2. This is the right side of 4. And the bottom of 2 is this point again. So all 8 of these points are actually the same point once we make all the identifications. And the interesting thing about this point is if I decide to make a trip around the point, so if I start going in a circle around this point, we can kind of, well, we see that at this point, I've kind of gone more than 2 pi, and I'm still not back to where I started. I keep going, and finally, I get back to where I started. And so if you add up all this, all the angle here, the angle should be 6 pi, which I could write as 2 pi times 2 plus 1, where this 2 is the number of excess 2 pi's. And so the nice thing about translation surfaces, anytime you have one of these singularities, which kind of shows up on the surfaces, they are all multiples of, the cone angles around these points are all multiples of 2 pi. And we can kind of keep track of the sort of the excess angle at each one of these points. Okay. Okay, so let me introduce an SL2R action. So there is an SL2R action on the space of translation surfaces. I haven't really told you what the space of translation surfaces is or what I mean by that. I will. In this action, SL2R action, it's just the normal linear action. And so if we're thinking about this object, this translation surface as being in the plane, I could hit it with, say, a matrix. And it's going to do exactly what it would do in the plane. So this is a shearing matrix. It's just going to shear us a little bit. So we're going to end up with something kind of like this. Okay, and just notice how like these two sides were identified, but since these sort of linear transformations take parallel sides to parallel sides, the identification is kind of respected. Right? So after these move, they're still parallel. The identification is still there. Okay. Great. So let me give a slight alternative or very alternative definition of a translation surface, which will make this whole maybe space of translation surfaces a little bit clearer. And what I mean by that. So a translation surface is a pair x omega, where x is a Riemann surface. Actually, I should say a little bit about to quantify this Riemann surface somehow. Qualify. Is a, how about a compact connected Riemann surface. And omega is a non-zero holomorphic, or if you like, abelian of the first kind, abelian differential. Okay. And so I just mentioned this for, well, a couple of reasons. One, I will, my notation above, I kind of dropped the Riemann surface, and I'm just hanging on to the differential, but it's just kind of my shorthand. So when you see omega, it's just a reference to the translation surface. So there's one more thing that I should mention here. So this the space of translation surfaces it is just the set. So I should be a little bit careful. Let me say it like this. We're going to fix the underlying genus. So let's just call it genus G of the Riemann surface. And then the pairs, I'm going to call this maybe HG, X omega, where X has genus G, and X omega is a translation surface, is this space. And this is actually a bundle over the moduli space of Riemann surfaces. So this just kind of projects to the Riemann surface. It forgets about the differential. Okay, and this is rank G. It's a complex G-dimensional vector space. Okay. Cool. Okay, so I'm not going to spend too much time on this perspective, but I did want to kind of throw it out there. Let's explain where that omega was coming from. I'm going to go ahead and jump to giving you the definition of superdensity. So this is something to do with the linear flow on the surface. Let omega be a translation surface. We say the linear flow. So remember, this is the translation surface is sort of a flat surface with these weird singularities. And the linear flow is just a trajectory in the north direction on the surface. And I'll say a little bit more about that in a second. So the linear flow is super dense if there exists a constant c greater than 0 such that for every t greater than 0, capital T is some time, the segment of the flow for t from 0 to capital T is within c over t of each point on the translation surface. So just maybe point out, I could change this, and I might to going from 0 to c times t, and then the segment being, let's say it in a different way, 1 over t dense. Okay. Let me kind of draw a picture of an, let me just start by giving an example of something that's not super dense. So this is just some quantitative density condition on the linear flow on the surface. So let's start with, so let's take a torus and then pick a rational slope on the torus. So we're going to say a slope of maybe 1/2, and this is going to define a certain trajectory on the torus. Okay. So maybe we end up with something kind of like this. And we can kind of look at this trajectory. Okay. So if this were, if this trajectory were super dense, then that would mean that I could find some c, so that if I make a neighborhood kind of around this point, around this trajectory, where the neighborhood has sort of this sort of c over t neighborhood around the trajectory, then I could do that for any t. So there is some constant where this would be possible. And we can sort of see that this can't happen for a periodic sort of trajectory like this, because as t goes to infinity, the trajectory is not spreading out in the space, but this neighborhood around the trajectory is shrinking. Okay, so at some point, the trajectory just kind of ends up being a very, the neighborhood around the point just ends up being a very skinny thing kind of around this trajectory. And it's just not going to cover every point on the surface, so it's not super dense. Okay. Let me give you maybe a slightly different example. So I should say one thing about this. You should complain. You should complain that I was talking something about like the flow being the north direction. So if I want to think about this not just as a torus with the trajectory on it, but as the translation surface that I want to have some associated Teichner geodesic attached to, or that's attached to it, then what I should really do is orient this so that the trajectory is in the north direction. So there you go. There's sort of the translation surface picture that I have in mind. Okay, so now let's do something slightly different. So I'm not going to do something periodic. We're going to say, let's pick the slope to be irrational. So slope, I don't know, pi. Okay, so I'm not going to worry about rotating this. but we have some slope that, I don't know, something kind of like this. So it hits here, and we'll start back on this side. And so I'm going to think about this one for just a minute. So I'm not going to, I'm not going to be able to show that this is not super dense. But what I will do is sort of suggest how you might go about doing that. Okay. So one thing that we can do is we could, well, let's just sort of say what superdensity would suggest. If this were super dense, then I could find, some C such that the CT, C over T neighborhood around the trajectory is always covering sort of the surface. And as it turns out, you can't find such a C for this. And so what that's going to mean is somehow if you think maybe there is a C, then you can travel out some capital T, and then just kind of assume that you've got this C sort of working, but then you could go a little bit further and see that somehow this is not covering the surface. And the way that you might go about doing that, you could take a section. So we have a linear trajectory on the torus. I just want to take a section over here from say 1 to 1 plus I, which is the same thing as I, and that's the same thing as 0. So on the surface, thinking about this in the plane, just take a section through here and observe when the linear trajectory is hitting it. And just notice that, let's see, at time t is equal to 0, we were at 0. And then at time, let's see, maybe I shouldn't say time, but at x value 1, we have moved up, let's see, we moved up pi. So we're going to hit the section at, well, 3.1 for whatever, but we're going to take the fractional piece of this. So that's just the fractional piece of the pi. Okay. And then if we do that again, we go over 2 x's. So that's going to hit the section again, and we're going to get the 2 pi. And if we keep doing that, what we're really seeing is how, maybe it's something you've seen before, but how this linear trajectory, when you take a section, it induces a circle rotation. And so that's kind of what's happening here. The circle rotation that we're seeing is x plus pi, and then these points that are showing up, just the orbits of 0. Okay. And so now what you can sort of say is, okay, well, if this thing was super dense, that means that this neighborhood that's surrounding the trajectory, that neighborhood is also hitting our section, which means there's a neighborhood. So there would be some neighborhood around each one of these points. And that neighborhood would have to cover the entire section, right? It'd have to cover that entire line or the segment. And what you can sort of show, or what you can maybe notice, is that, well, this is turning into some kind of approximation type problem with circle rotations, which might be connected to Dirichlet's the Dirichlet's approximation theorem. So let me sort of end with just a theorem which comes from the paper that actually motivated the result above. So Kinshin proved the following. So any half-infinite geodesic is super dense on the torus if and only if the slope of the geodesic is a badly approximable number. There's a certain subset of the irrational numbers that would actually produce these superdense flows. Badly approximable, maybe something to keep in mind. There seems to be a connection to kind of continued fractions here. So the badly approximable numbers are exactly the ones. So if alpha is badly approximable, we could extend it as a continued fraction. And you see that the AN, the set of ANs that are going to show up here, these integers, are uniformly bounded. So there is just some big bound B where none of these go above. So examples of that would be things like solutions, irrational solutions to quadratic equations. Okay, so with that, I'll go ahead and stop the first half. And I'll move on to the second half where we'll get more into the theorem.